We have identified four basic wave parameters: the wavelength, which we call by the Greek letter lambda, the frequency, or the number of wave crests per second that pass a given point, which we call by the Greek letter nu, and the period, the amount of time it takes for one wave to pass a given point, which we call capital P, and also the speed of the wave, which up to now we have called v, indicating a velocity for any speed whatsoever. But since we're going to be dealing exclusively with light, which travels at a constant speed c, is called the speed of light. It's equal to 186,000 miles per second, if we want to. Then from now on, we will call the speed of our wave by the letter c. Now, since speed was shown to be a distance over a time, then it was equal to the wavelength over the period. And we also established that the period and the frequency were in inverse relationship, that the period was 1 over the frequency, and the frequency was 1 over the period. So since c is equal to lambda over p, it's equal to lambda times 1 over p. But since 1 over p is mu, then c is equal to lambda nu. And this is our basic equation for a traveling wave. The speed with which it travels is equal to the wavelength times the frequency with which the waves pass a given point. Now I want to see what happens when you, who are recording the wave passing you, also have some motion. Now we're familiar with this in everyday life. For example, if you stand by a railroad track in a steady position, then you will hear a train approaching you, and as the train approaches you, then you will hear a change in the pitch of the signal as it comes, and then the pitch will get lower as the train goes away in the other direction. And this is called a shift in the frequency or the pitch, and we will investigate the formula by which you can determine the amount with which the shift is taking place related to the velocity or the speed with which the object is approaching you. So let's suppose that you are standing in one position, and suppose that you are on the crest of a wave. And suppose you have a friend standing in another position, and he is on the next crest of the wave. Now, if you're standing still, and the wave is traveling in this direction, then as the wave travels, your friend will approach you. And the amount of distance that your friend travels to approach you is therefore the wavelength of the wave. But now this changes if you are also moving. So suppose that you started in this position, but now you're moving forward in this position. And now your friend is sitting right on top of this wave, traveling right along with it, and after some amount of time he reaches you. But the amount of distance that he traveled to reach you is shorter if you're also approaching him than if you were standing still. So the distance between your position on the wave and the next position on the wave is now changed into some lambda prime. It's quite clear that if you're standing still and your friend is coming towards you, then there's a certain amount of time for him to reach you. But if you run towards your friend, at the same time your friend is running towards you, that reduces the amount of time it takes for the two of you to meet. And the opposite is also true. If you are standing on top of one crest of a wave, and your friend is standing on top of another one, and you start to run away in this direction, then as your friend travels along the top of this wave, it's going to take a longer time for him to catch you because you're moving away. So therefore, the lambda prime, which is the distance between the two wavelengths, is going to be extended. And the same is true if you're standing still and your friend is running towards you. It takes a certain amount of time for your friend to reach you. However, if you turn around and start running backwards, then it takes even longer for your friend to catch you. So that the time that it takes for one wavelength to reach another wavelength is extended. So this relationship is a way that you can measure the velocity, capital V, with which you are running, or the velocity, the capital V, that you are running in the other direction. So we call the velocity of the moving person, or the measuring device, by capital V. And there is a shift in the wavelength, which we call delta, which stands for change. The change in the wavelength is the new wavelength divided by the old wavelength, or minus the old wavelength. It's the amount that the wavelength has changed according to the fact that you're moving towards or away from a point on the wave. Now you are moving with a velocity v. The wave is moving with a speed c. The ratio between your velocity and the speed of the wave is the same as the ratio between the change in the wavelength that occurs because of your motion to the wavelength that is present if there is no motion at all. And this relationship is known as the Doppler shift. And it is what we use to measure velocities, because when the light comes in, we can measure the new wavelength lambda prime that we see. In the laboratory, we can measure the undisturbed wavelength lambda. So we can subtract the two to get our numerator. Then in the laboratory, we measure the undisturbed wavelength lambda, so we have that one as well. The speed of light is well known, so the only thing that we don't know in this equation is v. So we can use this equation to determine the amount of shift in a certain wavelength caused by the motion of the measuring device. Alternatively, if you can measure the amount of, if you know the amount of velocity that you have, you can use that to predict the amount of shift that will take place. So you can use the formula in both directions, and this formula is known as the Doppler formula.